Hello, I'm Eduardo, and I will be presenting a PolyFit, perception-aligned vectorization of raster ClipArt via intermediate polygonal fitting. The research was conducted at the University of British Columbia, together with Nico Shelter, Jonathan Griffin, Cheyenne Oshiari, Leonid Sigal, and Alla Scheffer. ClipArt images consisting of distinct color regions with clear boundaries are ubiquitously used in digital media. These images can be compactly and losslessly represented in vector form. However, for a range of reasons, many such images are stored in raster form, which limits their usage. For instance, the Adobe Stock Image Database contains over 9 million images labeled as clipart or icons. Algorithmically vectorizing these raster clipart images would facilitate a wide range of effective editing applications and enable resolution-free reuse of artwork created for legacy displays. Contrary to natural raster images, ClipArt images allow for a clear mental vector interpretation. Yet, existing vectorization methods frequently produce outputs inconsistent with viewer expectation. Several prior works focus specifically on vectorization of artist-generated imagery. Dedicated methods target upscaling and vectorization of low-resolution pixel art images. Notably, Kopf and Lishinsky focused on resolving topological ambiguities during segmentation, then fitting splines which are C2 continuous everywhere, except at T-junctions. Potrace computes a rough polygonal approximation, and then replaces it with a smooth spline, detecting seed-zero discontinuities using an angle-based heuristic. Unfortunately, their polygonal approximation results in the loss of fine details, which are not recovered in later stages. Recently, Oshiari et al. Proposed to identify the location of seed-zero corners on the pixel boundary using a learned classifier. This initial guess is then iteratively refined in a perception-motivated pipeline. Their method struggles with inputs of varying resolutions, and it's computationally expensive. Vectorizing a raster image requires a two-step process: segmentation and vectorization. Segmentation of raster clipart images into regions is relatively straightforward. However, vectorizing the raster boundaries between these regions while meeting observer expectations remains challenging. And this is exactly the challenge that we're going to address. Vectorizing raster boundaries requires fitting each boundary using piecewise smooth splines, consisting of a sequence of curved primitives. We consequently need to compute the number and types of primitives in the sequence, as well as the locations of the transitions between them. Therefore, our challenge can be formulated as finding this sequence of primitives well aligned with human expectation. Perception and computer graphics literature suggest a number of criteria that are likely to impact the process of mental vectorization. First is accuracy, which predicts that vectorizations are geometrically close to their input raster. Details are not hallucinated, respecting what you see is what you get principles. The Gesellschaft psychology principle of simplicity indicates that human observers prefer simpler explanation of observed phenomena. In the context of vectorization, simplicity argues for a lower complexity of the primitives and minimal curvature variation within each primitive. The simplicity principle also argues for more regular representations, indicating that observers prefer to group stimuli into regular patterns. Regularities that are visible in the input raster are expected to be preserved in the vector output. The Gesellschaft principle of continuity argues for vectorizations made of continuous curves with a minimal number of seed-zero corners. Previous research highlighted how important it is to identify all correct locations of such discontinuities, and how single misclassification can substantially disrupt the vector output. Converting this principle into an actionable algorithm requires understanding the interactions between them during the mental fitting process. Learning these interactions directly from pairs of raster images and algorithmically vectorized counterparts is not possible due to rasterization being a lossy procedure. Furthermore, manually creating these pairs is impractical, as vectorizing a single region requires 30 to 45 minutes of artist's time, making construction of large-scale training set problematic. The problem of vectorization shares many similarities with the problem of polygonal fitting. We can compute the desired vectorization by first approximating the input raster boundaries using coarse polygons, and then use this intermediate output to guide the rest of the computation. This choice is motivated by the observation that the approximating polygon human observers prefer is strongly correlated with their preferred piecewise smooth vectorizations. In terms of primitive counts and tangents, as well as corners and other transition locations. To compute the intermediate polygons in alignment with human preferences, we begin by constructing a graph of all possible candidate edges connecting points on the raster boundary. Our vertex placement logic was motivated by user study, where participants were asked to draw polygons approximating raster boundaries. The results of the study indicated that points were predominantly placed at pixel corners and middle of symmetric vertices. We use a similar observation and connect vertices along the raster boundary if the Manhattan distance is below 1 and all misclassified pixels are to one side of the edge. The extraction of the intermediate polygonal approximation is formulated as the problem of finding a cycle that minimizes an energy function defined on pairs and triplets of edges. The optimal cycle balances the perceptual metrics of accuracy, which promotes geometric proximity to the raster boundary, continuity arguing for lower curvature, and simplicity expressed as a preference for reduced curvature variation, as well as reduced edge count. The second stage of our algorithm fits a closed piecewise smooth spline to the extracted polygon. This requires finding the type of the primitives, their mapping to the raster boundary segments, and their control points. In order to uncouple the computation of these variables, we leverage the following observations. First, the seed-zero corners of the smooth fit are a subset of corners of the polygonal approximation. The polygon tangents are also strongly correlated with the tangents of the final spline, particularly in the vicinity of polygon edge midpoints. This observation suggests using edge midpoints as ideal candidates for G2 transitions between consecutive primitives. Furthermore, the polygonal and smooth fit are expected to provide a similar balance between continuity and simplicity. That is, we expect at most one seed-zero discontinuity between consecutive edge midpoints, and no more than two primitives. Following these observations, we designed a primitive space, which reflects all different choices in balance. The line-line primitive configuration is simple and accurate, but the most discontinuous. The curve primitive configuration consists of a single Bezier, which approximately linearly interpolates the tangents. It is the most continuous, but potentially least accurate. Finally, the curve line primitive configuration has the same primitive count as the polygon corner, providing an accuracy between the other two. To obtain the primitive configuration which best fits the polygon corner and underlying raster boundary, we use a random forest classifier. The classifier computes its categorization from the geometric information provided by the intermediate polygon, and 3 exemplary fits which incorporate the fact that spline fitting is a local global problem. This results in a total of 10 features, which are independent of the input resolution. The classifier is trained on 23 manually annotated models, in contrast with over 100 models of Oshari et al., and achieves 99.3% accuracy, using a 50-50 split between training and the testing set. After computing the per-corner primitive configurations, we then optimize the control points of all primitives to generate a spline well aligned with human expectations. We seek a spline S which minimizes the following objective function: an energy term promoting proximity to the raster points, a second energy term promoting alignment with the polygon tangents, and to produce a final fit which best balances accuracy, tangent alignment, and simplicity, we augment the energy with a shape term. This energy term minimizes curvature variation across primitives and enforces soft G2 constraints. To preserve regularities present in the input raster, it is not possible to add them as soft terms to the optimizations, since they need to be enforced exactly. Our focus is on symmetries, parallelism, axis alignment, and continuations, which are identified on the raster input as well as the intermediate polygon. Regularities are enforced at the polygon level through a combination of graph pruning and direct modification, and at the spline level through modifications in the primitive configuration classifications, as well as adding hard constraints to the final fit optimization. So far, our description addressed the baseline scenario of drawing consisting of two uniformly colored regions, but real-world data is comprised of multiple colored regions. We have extended our framework to handle multicolor data by ensuring consistent geometry across shared boundaries and in the neighborhood of junctions of valence 3 and 4. Similarly, many ClipArt images can have varying shading near inter-region boundaries, which are often caused by anti-alias rasterization. The boundary extraction stage of our method can be extended to handle such inputs. We refer to the paper for further details on these extensions. We will now show vectorizations obtained with our method compared to those of the existing state-of-the-art. Shown here is a comparison on a multicolor raster image. We can observe how Salinger fails to identify fundamental SID0 discontinuities in both insets, and loses small yet important details on the top part. Similarly, Oshari et al. Does not identify enough SID0 discontinuities in small boundaries near the bottom inset, but identifies too many on the top part. Here are the vectorizations on a highly structured input. Generally, Salinger's vectorization is overly smooth. Oshari et al., on the other hand, identifies more SID0 transitions correctly than Salinger, but the primitives are not aligned with observers' expectations, and irregularities, such as axis alignment and symmetry, are not preserved in the final output. Here we show an example of two extremely low-resolution inputs and the corresponding vectorizations. Note how pixel size details and axis alignment are lost in the vectorizations obtained with existing methods. Here is a relatively simple bitmap font. The outputs from alternative methods suffer from similar artifacts seen in previous comparisons. In particular, when the method of Oshari et al. Fails to detect SID0 discontinuities, it tends to over-regularize small raster regions into circles. We quantitatively assess our results by comparing them to algorithmic alternatives via a perceptual study conducted on the Amazon Mechanical Turk platform. The study was comprised of 1,190 questions across varying resolutions on binary as well as multicolor data. In the study, we compare our method to that of Selinger and Osciari on 81 inputs, including those provided by Osciari. We've also included Kopf et al. On a comparison on 28 additional low-resolution color inputs. Here we show the results of the user study. We can see that human observers prefer our method by a ratio of more than 3:1. At resolutions of 16 by 16 pixels or less, our method was preferred in 94% of the cases to that of the closest competitor. To conclude, we presented PolyFit, a new method for vectorizing ClipArt, a challenging type of input for existing vectorization methods. PolyFit performs particularly well on low-resolution data and is an order of magnitude faster than the state-of-the-art. Our key insight is to obtain an intermediate polygonal approximation aligned with human perception and leverage it to facilitate the final vectorization. Thank you for your attention, and we look forward to all your questions in the Q&A session.